So these are the notes, the limiting and excess reactant and BCA charts. So to start off, I'm gonna go through a little explanation that's going to kind of give you it's sort of like some examples and a analogy to sort of give you guys the concept behind what we're doing here, because I think if you understand what is actually happening in real life, it makes a lot more sense than when you go to do the numbers. All right. So I'm going to kind of try to walk you through the concept of what this is all doing, what it's actually doing in real life. So hopefully it'll then make sense when you go to run and plug the numbers. Okay. So, so first off, if we have a chemical reaction like this, right? 2H2 plus O2 yields 2H2O. What are the things on the left? Generically, what do we call those? Everything on the left of the arrow, yeah. Reactants, good. So these, and yes, I will post this online as well. So we call these the reactants. Now, if you look at your paper, there's a word that's reagent. That's the same as reactant. So if you see the word reagent, that means the same thing, okay? So reactant or reagent. What about the stuff on the right side? Anybody remember what those are referred to as? The stuff being, yeah, good, product, the stuff being produced. So this is the product or products on the right side, right? Okay. So we have the reactants, which is, or what's there before the reaction, and the products which are made after the reaction, right? Now, if we think about a balanced chemical equation like a recipe, right? The reactants are like the ingredients. The products are like the final product or whatever. So if you have your ingredients and you're making a cake, the reactants would be like the ingredients going into it. The cake would be like the product, right? And you've got, the recipe tells you how much of each thing you've got to put together to get a certain product, correct? That's like a chemical reaction. So this balanced chemical equation is telling us we have two molecules, or moles if we're thinking that way, of hydrogen plus one molecule of oxygen are going to produce 2 molecules of water, right? Now, so this is like a reaction. Now, imagine, go back to the idea of a recipe. Okay, so if we have a recipe, and again, I know, don't judge me for my fake recipe. That's why I'm a chemist and not a cook. But let's say we have a recipe: 3 eggs plus 2 cups of flour plus 1 cup of sugar gives us 24 cookies, right? Okay, so 6 eggs. If we had 6 eggs, how many cookies could we make? 48. Why do you say that? Why? So you're not wrong. Why did you decide? Yeah, good. So what he's saying, you notice, is that the number of eggs, with 6 eggs, you can run the recipe twice, right? We can do this recipe twice. So if we do the recipe twice, you would get the product twice, or we would double it. So 24 cookies would give us, or I'm sorry, 6 eggs would give us 48 cookies, right? Now, let me show you something. So if we took six eggs, we did a conversion. We know eggs here, and we want to know how many cookies. Okay. Our recipe tells us that for 3 eggs we make 24 cookies, right? So 6 times 24 divided by 3 is 48 cookies. So you could use the dimensional analysis factor label method to figure out how many cookies. Now, are you going to do that? No, like in your head, like it's pretty easy to look at, like you guys, like a lot of you guys did, and you just look at it and say, okay, it's double, so we just double it, right? So you don't need to go through this. But the concept is, this is really what you're doing. You're doing a conversion, sort of, using a recipe. Okay, now it doesn't just work from from the ingredients to the product. It can work the other way too. So, for example, what if I told you we want to make 12 cookies? How many cups of flour would we have to use to make 12 cookies? Why 1? Yeah, good. 2 cups of flour get 24 cookies. So if you want to do half of that, you divide that in half, right? Well, look here, you can do the same thing. We know that it's 24 cookies, and for that we would need 2 cups of flour. So we would do 12 times 2 divided by 24 would tell us 1 cup of flour would be needed. Make sense? Okay, if I hit a thing or something where if something's not making sense or you have a question, please ask, okay? Because I'm going to go through this and I kind of assume that it makes sense, but if something doesn't, ask, because I'm sure a lot of other people have questions too. All right, so 12 cookies would give us, or we would need 1 cup of flour to do that, right? Oh, shoot, I already had cup in there. Okay. So far, so good, makes sense? That's the same concept of what you guys have actually been doing with your stoichiometry. So, does anybody have theirs out? Or you do? So, if we look, like,
I don't have the, like...
No, you're good. Okay, so if we look at one like 14, okay, now we're using the equation, but she has here, but basically we had 0.77 grams of H2O. Okay, and actually I do want to look at that real quick. Let me see.
Did I do something wrong?
No, I just want to see if it's okay. So if you have 0.77 grams of H2O, and you were turning it to, oh, you accidentally doubled it. That's okay. So if we have 0.77 grams of H2O, right? That's the amount of water we produce. If they want to know what mass of hydrogen peroxide is needed, you just convert to this using the number that we had, the amount that we had here. So if we know one amount of these, we can figure out the amounts of anything else just by running it through the conversion. Okay, so that's just like a recipe. Okay, so now what does that have to do with what we're doing here? What if I gave you guys this? What if I said you have 9 eggs, 10 cups of flour, 10 cups of sugar? How many cookies can you make? What would be the most number of cookies?
72.
Why?
Because you're multiplying the things by the eggs. You can do it's like times 3, Even though the other ones are like times more, you need to have like the same amount.
Yeah, you're totally right. So the eggs, we can run the recipe 3 times, right? Because you need 3 eggs each time. So we can run it 3 times, which gives us 72. How many times could we run it with the flour?
Wait, 8.
No, not. We got 10 cups. 5. There you go, right? 5 times. Because it takes 2 cups each time. So 5 times 24 would be 120. Thank you. 120. How many times could we run it with 10 cups of sugar? 10 times. Good. So those are the amount of cookies we could make if we used all of each of the, or not of each of, if we used all of that ingredient, right? Why is it only 72?
Because you can't make more if you don't have
One of the ingredients,
yeah.
right? Yeah, there you go. So if you don't have it, so once we hit 72 cookies, we run out of eggs. You can't keep doing the recipe without one of the ingredients. So the eggs you run out of first. This is called the limiting reactant when we're talking about a reaction. So here, the eggs limited, because we ran out first, the eggs limited how many cookies we could make. That determined it, right? So a limiting reactant in a chemical equation is the substance in a reaction that is completely used up first. Once the limiting reactant is gone, the reaction cannot continue, which means that the limiting reactant controls how much of all the products that can be made. Because when you run out of it, the reaction has to stop. The limiting reactant also determines how much of the other reactants are used. So for example, if we go back to this recipe, if we said we're using 9 eggs, because that's the thing that runs out, how many cups of flour do we need to use? Okay, 6. Good. How does that happen? Well, we know we have 9 eggs, right? That's what's going to run out first. We know that we use 3 eggs. Each time we use 3 eggs for the recipe, we use 2 cups of flour, right? So 9 times 2 divided by 3 means we would use, in order to use 9 eggs, we use 6 cups of, we use 6 cups of flour. So you can also figure out how much would be left over, right? Take the amount you start with, the 10, subtract the 6. We'd have 4 cups of flour left over. All right, so are we okay, like concept-wise, like how these ideas? All right, now let's talk about them in terms of chemical equations and stuff. Like why am I using the recipe example? Okay. Up until this point, we've really been just talking about balanced equations and doing like the exact amount. So in other words, if we go back to the worksheet you guys did for today, and we looked and we saw, in this one, if you used 0.87 grams of oxygen, you would, or if you got 0.87 grams of oxygen, you would use 0.87 grams of O3. Like that would be the exact amount of reactant and the exact amount of product. In real life, having the exact amount of all the reactants to perfectly use all of them up is very rare. Okay, let me give you an example. You burn wood in a fireplace, right? So it's called the combustion reaction. When does that reaction stop, or what causes it to stop? Wood burns up, right? Wood burns up and is gone. So a combustion reaction is the fuel, the wood, plus oxygen from the air. Did we use all the oxygen in the air? No, like there's plenty of oxygen. It doesn't make sense. So we had plenty of oxygen left over. It wasn't like we had exactly the right amount of oxygen just to use with the wood. We had way more than enough. So the wood is what we would call the limiting reactant, the thing that runs out first, which stops the reaction. Makes sense so far? Okay. The excess reactant or excess reagent is the substance or substances in a reaction that are not fully used up when the limiting reactant runs out. So in our burning wood example, that would be the oxygen. The oxygen we had excess, we had more than enough. Okay. In our recipe example here with these, what would the excess reactants be? Flour and sugar, the things that we had left over after it stopped. Everybody good concept-wise? Questions? Okay. So we have limiting reactant, the thing that runs out first. We have excess reactant, reactants that are left over after the reaction stops when the limiting reactant runs out. Okay? Those are all reactants. That's on the left side. All right. So let me switch to this version of these. You can. So the highlighting I just highlighted to link like the parts. So BCA chart. The B stands for before the reaction. That's the green highlight. The C stands for the change during the reaction. And the A stands for what's left after the reaction. So I just highlighted those to kind of link them. You should add this. All numbers in the chart are in moles. You should add that. That's super important. Okay, it says it up here in the before reaction thing about being in moles, but it's really important. In the chart, all the numbers are always in moles. If they're not in moles, then you need to convert them to moles. Okay, it's super, super important. All right. So this walks through each part of the chart, what you would need to do. The easiest way for me to kind of do this is to walk through an example with you. So I'm going to go back and forth. You can, if you want to just turn to the example part, you can, and just kind of watch up here when I go back to this, whatever you want to do. All right. So the first example problem is a problem that we do when we're just trying to find out what's the limiting reactant. So we're trying to find out what runs out first. Okay. So in the before, the number of moles go on this line, on the before line. You will have zeros for the products because the reaction hasn't happened yet, right? So you won't have any products. So now when you look at this, the examples on the back side are a little better lined up. That middle line on the BCA chart is supposed to split reactants and products. It's supposed to line up with the arrow. When I printed them off when I converted it, I think it's shifted it a little, but so this is supposed to be reactants on the left, products on the right. This line is supposed to be basically where the arrow is. Okay. So 10 moles of H2. So I'm going to put a 10 here. I'm going to shift it over just a little bit. Okay. That's for the H2. The O2, 7 moles. Okay. Notice I'm not even putting oh, sorry, you can't see that. Notice I'm not even putting labels on them. I'm not even putting labels because everything in the chart must be in moles. All of it has to be moles, okay? Now, water is a product. All products are going to be 0 before the reaction happens. Okay. Everybody good so far? Okay. Now, if particles or mass are given, then you convert to moles to get moles to do that before one. To determine the limiting reactant, take the number of moles on the before line and divide by the coefficient for each reactant. We're determining the limiting reactant, so we're only looking at the reactant side. So we take the number of moles. So for the limiting reactant, we take the moles, so 10 moles of H2, divide by the coefficient in front of the H2 in the balance equation. So there's a 2. Okay, so this is the coefficient from here. Okay, so 10 divided by 2 gives us 5. We do the same thing for every reactant. So O2, so we start with 7 moles of O2 divided by coefficient. There's nothing in front of it, so it's a 1. Okay, so that's just 7. Now, you compare and the smaller number indicates the limiting reactant. You compare the answers, and if there's more than 2, there's 3 or whatever, you compare the answers, and the smaller number indicates the limiting reactant. So the smaller number here is 5, which means our limiting reactant, or the thing that ran out first, was what? Hydrogen, the H2. So limiting reactant equals H2. And that's the answer when it's asking for limiting reactant. Okay. This stuff isn't hard in terms of like the math you're doing or like whatever. It can be confusing though, and that's why I tried to give you the explanation for what's happening behind it to help you. You just really have to stay organized, watch your labels as you go through stuff like that, okay? All right. Let's set up so for this one, if all they ask for is a limiting reactant, you actually don't even really need the BCA chart. You just need the moles of each reactant and then divide them by the coefficients and then compare the numbers, okay? All right, let's take a look at the second one. We'll at least get some of this set up here. The most important commercial process, blah, 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 blah. All right, how many moles of NH3? So this is asking us for, it wants to know how many moles of NH3 can be formed from 3 moles of N2 and 6 moles of H2, given the following balanced equation. Okay, so our before line, the B row, that's, again, always in moles, which these are given to us in moles, so we don't have to convert. So for the nitrogen, 3 moles for the nitrogen. For the hydrogen, 6. Okay. Now, what do I put under the NH3? Okay. 0. Good, because remember, it's a product. There are no products before the reaction happens. So far, so good? Okay, we need the limiting reactant. We got to figure out which one of these runs out first. It didn't ask for it, but we still need it to figure out how much of something we're going to get. So I take each of these, the limiting reactant, I take my beginning number of moles of N2 divided by the coefficient in front of the N2, which is just a 1. Okay, I do the same thing for H2. So 6 moles of H2 divided by my coefficient in front of the H2 is a 3. So I get, so what's my limiting reactant? H2. That's so you compare these numbers. The smaller one is the limiting reactant. So H2 is what runs out first. Everybody okay? So, oh, not H2O, just H2. All right. Everybody okay so far? All right, now, the change row.
Pardon the interruption. Foods 2 students, please remember to stop by Mrs. Liska's room for your lab ingredients on the way out today.
Okay. All right, so to finish this off, so at this point, we figured out that the limiting reactant is H2. Okay, now, here's what we do with that. To get the change rho, the change during the reaction, use the coefficient for each reactant and product, then multiply by the number of moles of the limiting reactant. In other words, the smallest number that was used to determine the limiting reactant. So, you don't have to write this in the chart like, excuse me, like all the time. I'm going to put it in here just to kind of show you. So to get the change rho, you take the coefficient times the limiting reactant number. All right. So the coefficient, so if I look at the N2, the coefficient is 1. My limiting reactant number, the number that showed us the limiting reactant, was 2. So 1 times 2. Okay. For H2, 3 is my coefficient times 2. This number, the limiting reactant number, is always the same. It's the same number each time, and you're just multiplying it by the coefficient. So for NH3, it's going to be 2 from the coefficient times 2. So for the change rho, we get 2, 6, 4. That's how you do the change rho. Now, the after rho, this is the after the reaction. This is actually really super easy. All you do is you subtract the reactant side amounts from the before minus the change rho. So 3 minus 2 is a 1. 6 minus 6 is a 0. Okay? And then you add the product side. So 0 plus 4 is 4. Okay? Now, one thing that you can do that's a quick check on this is, remember, we have the limiting reactant we said was H2, right? So if it's the limiting reactant, that means it runs out first. So after the reaction is finished, there shouldn't be any of that left over. It should be 0. Now, sometimes because of rounding with different numbers, it might not come out to be exactly 0. It might be like 0.003 or something like that. That's okay. You can just make it a 0. But if you get something that's not even close to, like not really close to 0, then you probably did something wrong. Okay? Okay. So, remember, everything in this chart is in moles, right? So this A rho is what's left after the reaction is completed. This is telling us we have 1 mole of N2 left over. Our hydrogen got all used up, and we created or produced 4 moles of NH3. Okay, so the question here being, how many moles of NH3 can be formed? Well, moles of NH3, that is this right here. Okay, so our answer, 4 moles of NH3 can be produced. Okay, so that's the end of this example. Hopefully any of the classes that did not get to finish this example were able to forward to the end and this makes sense and you're okay on this. I will do the other 2 examples, but I'm going to do those in a separate video. So people just wanting those can just go to that video. All right. If you have questions, let me know, please. Thanks.